All right, ladies and gentlemen, welcome back. Today we're going to start off by finishing up some notes from section 4.3 day 1, and then we will move on to the day 2 note sheet where we're talking about some new stuff. But first, I want to go back to these day 1 notes because I want to talk a little bit more about looking at a function and determining its concavity. So let's take a look at this last example from the day 1 note sheets. Use the graph of the function f to estimate where f prime and f double prime are going to be 0, positive, and negative. And what this is really going to come down to is you remembering what each of these values, positive, negative, and 0, for f prime and f double prime tell you about this graph f. So one thing before we start to answer any of those questions, I put arrows at the ends of this graph of f just so it'll make writing our intervals a little bit easier. So now let's go back and let's talk about what each of these mean. Okay, so if you know that over some interval that f prime is positive, well, what does that tell you about f? Well, it should tell you that f is increasing. And so all I have to do now is look back at my graph of f of x and say, where is this graph increasing? Where is this graph going up? And so if I zoom in here, right, I would say that f of x is going to be increasing from negative infinity all the way to negative 1, and then from 1 to positive infinity, right? On both of those intervals, f is increasing, right? I can also say on these two intervals, if I pick any point and draw my tangent line, right, its slope would be positive, right? So those are going to be my two interval answers here. And so that's going to be negative infinity to negative 1, union 1 to positive infinity. Okay, so where is f prime going to be negative? Right? Well, if f prime is negative, that means that f is going to be decreasing, right? So we take a look back at f of x and we say, okay, where is f going down? And I would say that's going to be this middle part from negative 1 to positive 1. And so that is going to be, whoops, my answer there. And now you'll notice on all of these intervals I've written so far, I've gone with parentheses. And the reason for that is because I want to separate these intervals from the last question, which is where is f prime going to equal 0? So where does f prime equal 0? That's going to be wherever f has horizontal tangents. And that to me looks like at negative 1 and at positive 1. We have two horizontal tangents there. So for these are not going to be intervals. These are just going to be x values, negative 1 and positive 1. Okay, so again, important to remember, if f prime is positive, what does that tell you about the graph of f? If f prime is negative, what does that tell you about the graph of f? Same thing now when it comes to doing the same sort of question, but now we're going to talk about f double prime. So if f double prime is positive, what does that tell us about the graph of f? It tells me that f is going to be concave up on that interval. And now this is where we have to do a little bit of approximation here, but I should be able to look at this graph and say, where is this shaped concave up? So remember, for concave up, think of something like x squared, my half pipe analogy from yesterday's video, right? And I would say from somewhere around 0, and then it kind of has that, parabolic shape-ish all the way to infinity, right? It's concave up the entire time, okay? And so I would say about 0 to infinity. Do I know for a fact it's starting at 0? No, but you're allowed to make a little bit of an approximation here, okay? So I would say on that interval, f is concave up, right? And now where is f double prime negative? Well, that's where f is going to be concave down. So I'm going to do a little copy paste here to help myself out. So I'm looking for where f is concave down. So if I'm looking back at this graph of f of x, if I zoom back in on this graph, where does it appear to be kind of like an upside down parabola, negative x squared, right? So it looks kind of like that. I would say from negative infinity all the way till 0, right? It has that shape, that concave down shape, that upside down half pipe, right? So negative infinity to 0, right? And so that means then at 0, right? And again, this is an approximation, right? I'm looking at this graph and I can say it's somewhere around this point the concavity is going to change. And so I would say at around x equals 0 is where the switch happens for this function from concave down to concave up. Now, I could do what we did yesterday. I could do the concavity test and determine for sure that that's where the point of inflection is going to be. But I didn't really give you an equation here, right? I just gave you a graph, so a little bit of approximation is okay here. Okay, so if you have the graph of f, right, you should be able to tell me where f prime and f double prime are positive, negative, and 0 just by looking at the shape, okay? But a slightly trickier question is, what if the graph I give you is not of f, but of, let's say, its derivative, f prime? So here's what I'm going to do. I'm going to take this same graph, and I'm going to copy, and I'm going to come down here to this blank page, and I already have some questions set up here. And whoops, let me try that again. Paste image. Here we go. Can I get rid of those? No, that's fine. Okay, now we're going to change things up here a little bit. And this is no longer going to be the graph of y equals f of x, but now this is going to be the graph of y equals f prime of x. So if I give you the graph of f prime or f double prime of x, you should still be able to answer some questions. This time we're going to answer some questions about the function f. Now, I'm going to come back to this real quick. If you recall back in chapter 3, right, we spent a couple of days on graphing derivatives and graphing functions from derivatives. So one option you always have here is if I give you the graph of f prime, you could just try to graph f of x, right? Now remember, there are infinitely many possible graphs of f, right? Because we can shift the graph vertically. So, the y values don't really matter when we graph f given f prime. And so focus on the shape if you want to go that route, okay? But I'm going to focus on just this graph of f prime of x. So f prime of x can tell us a lot of things about f of x. Okay, so if I asked you, given that graph of f prime, where is f going to be increasing? Well, like we said above, right, f increases where f prime is positive. So I can look back at my graph now and I want to know, where is f prime greater than 0? So again, this is the graph of f prime. So be careful. You're not going to look at where this graph is increasing, right? To say where f is increasing, you have to look at where f prime is going to be positive. And that to me looks like we have an interval from -2 to 0. It's positive. And then from +2 to infinity. So from -2 to 0 and +2 to infinity. On both of those intervals, f prime is positive, so that is going to tell me where f is going to be increasing. Now, what about f decreasing? Well, f decreases wherever f prime is negative, right? Wherever f prime is less than 0. And so, if I take a look back at my graph of f prime, where is this graph negative? So let me unhighlight those, right? It's negative from -infinity to -2, and then from 0 to 2, right? On both of those intervals, f prime is negative, and so that is going to be where f decreases. -infinity to -2 and 0 to 2. Okay, so we can determine where f is increasing, decreasing, right? If we can look at our graph of f prime and figure out where it's positive or negative, right? And basically what I'm doing here is like we did back in section, I believe that was 4.2, right? When we're figuring out increasing and decreasing intervals, we would do the first derivative test, right? And we would check an interval and try to figure out where it was positive or negative, right? We're doing the same thing here, but graphically. So let's apply that same idea of the first derivative test, but graphically, to figure out where f is going to have local maxes and local mins. So what does it mean for f to have a local max? Well, think about that table you make when you do the first derivative test, right? We look and see, where does f prime go from positive to negative values, right? Where does f prime go from, that means where f is going to go from increasing to decreasing, right? That's how we make a peak, and that's going to give us a local max for f. So if I look at this graph for f prime, right, where does this graph go from positive to negative values? Again, I'm not looking to see where f goes from f prime goes from increasing to decreasing. I want to see where f prime goes from positive to negative values, and I see one place where that occurs, and that's going to be right here in the middle at x equals 0, right? At x equals 0, f prime goes from positive values. So again, right, I'm tracing along this graph, right? Those are positive y coordinates, and then after it, I have negative y coordinates, right? So wherever f prime goes from positive to negative, f is going to have a local max. How about a local min? Well, when I do the first derivative test and I'm looking at that table, that's where f prime goes from negative to positive values. And so now if I look back at my f prime graph, right, where does f prime go negative to positive? That's going to be at -2 and +2, right? That is where f will have local mins. Okay, so 2 local mins for f of x, 1 local max for f of x. Okay, let's talk about f's concavity, right? Now, normally when we deal with concavity, we do the concavity test, right? If I want to know where f is concave up, that's going to be where f double prime is positive. But if we scroll back up, right, if f double prime is positive, that means that the first derivative is increasing. So what I can do is I can look at my graph of f prime and see where it is increasing, right? Where f prime increases, its derivative, f double prime, is going to be positive, right? So if I'm looking at this graph for f prime of x, where does this graph increase? And you should notice a similar answer here, -infinity to -1 union 1 to infinity. Sorry, that infinity got a little smushed there at the end. There we go. Okay, right? F double prime is positive, right? That means that f prime is going to be increasing. And so if I look at my graph of f prime, where does it increase? -infinity to -1 and 1 to infinity, which you'll notice is the same answer as what we got up here, right? And as a matter of fact, all of these answers are going to be repeated down here. F is concave down, where f double prime is going to be less than 0, which means that f prime is decreasing. So on what interval or intervals is this graph increasing? Well, I only see the one interval, -1 to +1. Same answer from above. And now, where does f have points of inflection? So this is where f double prime is going to change signs. So it doesn't matter positive to negative or negative to positive. We just need any sort of sign changes, right? And so really a little shortcut for this is what you're really looking for is where f prime has extrema, right? Maxes and mins, right? Because, right, at -1, right, this is where f prime is going from increasing to decreasing, which means f double prime is going from positive to negative, which means f's concavity is changing, right? And then the other answer is at +1. This is where f prime goes decreasing to increasing, which means that f is going concave down to concave up, and that means it's another point of inflection. Okay? So you can tell a lot about a function just by looking at its shape. Okay? And now with these sorts of questions, you really have to just try to focus on, what function's graph are you given, right? And from there, what does that function tell you about the function that the questions are about? Sorry, that came out a little weird, but again, the focus here is here's the graph of f prime. What does f prime tell you about f? Well, actually, it tells you everything about f, okay? Right? If this is the graph f, right, well, what can you do with the graph of f to get stuff about f prime? Well, remember the relationships, okay? Same thing with f to f double prime. Okay, so now let's take a look at section 4.3 day 2 notes, and we are ready to talk about our main new topic for today, which is going to be the second derivative test. Okay, so let's skip this first example here and we'll keep it moving down, okay? And we're going to take a look at this graph here, f of x, this purple curve, okay? So this graph kind of looks like negative sine of x, which is its basis, but that's not really the main thing what we're going to look at here. Let's get right into it. What is the second derivative test? So here's what the second derivative test says, okay? If f prime of c equals 0, so there's some c value for my function, right, in its domain, okay? If the derivative is 0 for some function, we call that c value a critical number, right? So let's say we have a critical number and f double prime of c is less than 0. So at my critical number, right, if the second derivative is less than 0, that means it's concave down at that critical number. Well, I want you to think about what that looks like. Take a look at my graph back up here of f of x, okay? So take a look at this graph. First of all, where do you see a critical number? And secondly, where do you see a critical number where it's concave down? And there's only one place on this graph where I see a critical number and the shape of the graph is concave down, and that's going to be up here at 3 pi over 2. Okay, so the first thing, right, again, critical number comes first, right? What is f prime of 3 pi over 2, right? If I draw a tangent line here, right, the slope of it is 0. F prime of 3 pi over 2 is 0. That means there's a critical number here. Secondly, what is f double prime at 3 pi over 2? Now, ultimately, I don't care about the value of the second derivative at my critical number, right? I mainly just care about the shape here, right? I want to know, is it positive or negative? If I'm looking at this part of the graph, clearly it's concave down, right? Which means f double prime of 3 pi over 2 must be less than 0, right? Which gives me concave down at that x value. And so, if I'm looking at a critical number where the shape of the curve is concave down, So think about it. Shape of the curve is concave down. At the critical number, what must that critical number be? That critical number must be a local maximum. Okay? There's no other possibility here, right? If you are concave down at a critical number, then there must be a local maximum there. Okay? There's, again, no other option, right? Try to graph it. Graph any curve that's concave down, right? Make a critical point on that curve. It's going to be a maximum. Okay? Okay, so that's the first thing we get from the second derivative test. If you're concave down at a critical number, then there is a local maximum at your x value, which we called x equals c. Okay, well, what if we reverse the concavity? Okay, so let's look at some other value, right? Again, we're going to start off with a critical number, but this time, what if we are concave up at that critical number? If you have a critical number and you know your function is concave up there, right? You check the concavity at your critical number, whatever that x coordinate is, you get a positive, right? Well, again, let's look back at my graph. Find me a point on this graph where it's concave up and there's a critical number there, and the only point I see that matches that is going to be at x equals pi over 2, right? So the first thing here, is this a critical number? Yes, when I draw my tangent line, it is indeed horizontal. F prime of pi over 2 is 0, indicating I have a critical number here. And now, what's the second derivative here? What is f double prime of pi over 2? If I take a look at the shape of my curve here, right, that indeed looks concave up to me. F double prime at pi over 2 is greater than 0, which means we are concave up at our critical number. And so at that point, there must be a local min. Okay, right? So again, look at my graph of f of x here, right? Its local max is where it has a critical number and it's concave down. The local min is where it has its critical number and it's concave up. Okay, and so let's summarize this down here, right? If f prime of c equals 0, so again, that means a critical number of f. F double prime of c is greater than 0, that means f is concave up, right? Then there is a local minimum at x equals c. Okay, so this is essentially what the second derivative test is. It's another way of determining whether your critical number is a local max or a min. Remember, the first derivative test, right? You take your critical numbers, you split up your domain into those smaller intervals, and you check the value of the first derivative, right? And you look for sign changes. Positive to negative sign changes on f prime means that f has a local maximum there, right? F prime goes negative to positive, that means f has a local minimum there, right? What the second derivative test says is, okay, you're still going to find critical numbers, but instead of checking those intervals, what you're going to do is check the concavity at those critical numbers, and that can tell you if you have a local max or a min. Now, there is one thing I do want to add here that's going to be very important, okay? If f prime of c equals 0, so again, that means we have a critical number, and f double prime of c, so if I plug that c value into my second derivative and it gives me 0, then the second derivative test fails. Bum, bum, bum. Okay, this is the one downside of the second derivative test. Okay, if your second derivative turns out to equal 0, right, the test fails because it's inconclusive, okay? You have to go back and use the first derivative test. Okay? So again, the only downside of the second derivative test, right? If the second derivative happens to be 0, right, at your critical number, right, meaning that there is no concavity there, right, that means the second derivative test fails. So sometimes that's going to mean there is no local max or min there, which, hey, that's possible, right? It's possible for a critical number to not give you a local max or a local min. We've talked about that in the past, right? But what's happening here, right, is, since we can't determine the concavity, right, we can't say that it's going to look like, the graph is going to look like it does up here at pi over 2 or 3 pi over 2. So we can't say if it's a local max or min. So we have to go back and check those intervals, okay? So this is the only downside to the second derivative test, okay? Okay, so we've talked a lot about it. Let's see this in action. Okay, find the local extreme values of f of x equals x cubed minus 12x minus 5. So, finding local extreme values, finding local maxes and local mins. Well, the good news for us is we've done these steps, right? 4-step process, which we've done. Step 1 is always the domain, right? My function here is a polynomial, so my domain is all real numbers. Okay. Step 2, we need critical numbers. We absolutely still need to find critical numbers. That has to happen no matter what. Anytime you want a max or a min, you should think critical numbers first. So let's take the derivative of this. We get 3x squared minus 12. Set this equal to 0. Set this equal to does not exist. I already have none written here because this is a polynomial. This is going to exist. And yes, you must still be writing that out, even if you know in your head that you're not going to get any critical numbers from that. Okay, so set this equal to 0. I'm going to go ahead and factor this while we're up here. Factor out a 3. We get x squared minus 4. Right, set that equal to 0, you're going to get plus or minus 2. So I get 2 critical numbers here. Okay, so this is where you have a choice, okay? Anytime, and now this is going to be true for the rest of this chapter and the rest of your calculus life. When you get asked to find a max or a min, right, you get those critical numbers first, but now you have a choice. If you prefer the first derivative test, great, stick with it, okay? You can keep using the first derivative test as much as you want, but I'm going to show you how the second derivative test works because in a lot of cases, I think the second derivative test is easier and it'll save you time, okay? So how does the second derivative test work? Step 3, SDT, second derivative test for short. Well, first of all, find the second derivative. And the reason I like second derivative test on this example is because this is a really easy function to take the derivative of, right? F prime of x you find easily using the power rule. And now what's the derivative of that? Well, you guys are good at the power rule, right? So let's just do it again. We know f double prime is going to be 6x. And now I'm going to take my 2 critical numbers and I'm going to plug them into my second derivative. So f double prime of 2, right? So if I take 2, plug it into 6x, ultimately I don't really care about what the value of this is. What I care about is that I know it's definitely going to be a positive. And this tells me that my function f is concave up at a critical number. And so if f is concave up at a critical number, the second derivative test tells me that there is a local minimum at that x value. Do the same thing at my other critical number, f double prime of negative 2, plug it into f double prime of x, right? 6 times negative 2. Ultimately, I don't care about evaluating it. I care that it's going to be negative there. And that means that f is concave down at my critical number. And if you're concave down at a critical number, that means you're looking at a local maximum for your function f. So you could have taken +2 and -2, right? Split up your domain into 3 intervals, right? Picked a number from each of those intervals, plugged them back into f prime or the factored form of f prime. This is not even the fully factored form of f prime. I could have kept going, right? Or I could have found an easy derivative and just done a pretty simple product and determined where it was positive or negative. So I like the second derivative test in a lot of cases for determining when I have local maxes and mins. And now step 4 is to actually find the extreme values. So now I need to take 2 and -2 and plug those back into the original function, right? So 2 cubed is 8 minus 12 times 2 is -24. So that's -16 minus 5. I get f of 2 is -21. -2, go ahead and plug that in. I'll get -8 plus 21. Plus 24 is going to be 16 minus 5 is 11. And so, right, f of 2 is going to be, well, at 2 I have a local min, right? And so -21 is the local minimum value for this function. And at -2, second derivative test told me I have a local maximum. And so 11 is the local maximum for this function. Okay, so really the only thing you're changing when you do second derivative test is step 3, right? Step 3 is the main thing that changes. Steps 1, 2, and 4, when you're finding a local extreme, right, whether the question says, right, extreme values, local extreme, absolute extremes, right? Steps 1, 2, and 4 do not change. The only change is in step 3. And from this point forward, I want you to practice second derivative tests in tonight's homework, but from this point forward, you can really choose whatever derivative test you're most comfortable with. Okay? So that is it for section 4.3, and I will see you next time.